our goal for today is to sort of get an answer to the question, what's the derivative of our multivariable function? Because we have a partial answer in that we have this notion of partial derivatives. But it doesn't quite feel completely satisfying. So we'd like to dig a little bit deeper and say, okay, what's going on? How should we think of a derivative? And what are some things we can do with it? Well, let's begin. Now, the way we're going to start figuring out what we should be doing is to say, let's go back to single variable calculus. Because that's oftentimes the way we build up our understanding. It's like, well, let's go back to what we did before and see how do we generalize it. So we have our tangent line, and it has what? Y minus the function f of a is f prime of a times x minus a. This is called slope-intercept form, right? Our slope being f prime of a, and our point a comma f of a. Well, we have what we can call the tangent plane in multivariable calculus. What does it look like? Well, z minus the value of the function, so we can call it f of ab, is f of x of ab times x minus a, f sub y of ab times y minus b. And then we say, ooh, it kind of feels like a dot product. Now, why do we say that? Well, it's a series of things multiplied, but then you're adding them all up. That's what dot products do, right? You start with two vectors, you multiply the entries together, and you add them all together. So what we can do is you can say, oh, so I can think of it as a vector, which I'll call f sub x at ab, f sub y at ab, times x minus a, y minus b. And if you think about what's happening here, it's very similar. See, look at this part, x minus a. It's really, another way to think about it is change in x. So it says, if I'm trying to understand what's happening to the function, it looks like the derivative times the change in x. Well, here, we're saying, hey, it's kind of similar. But now you have a change in x and a change in y. So what we can do is we can take this new vector, which consists of our partial derivatives, fx, fy, and multiply by this vector that looks at change in x, change in y, and that's telling us what our change should be, at least approximately. So this new vector is the important vector. And so we give it a name. Upside down triangle f. Well, actually, that's not the name. It's called the gradient. So the gradient vector of a function is the vector which consists of the partial derivatives. And so, in essence, you can think of, to think of our derivative, we're going to have the gradient be our stand-in. And what it is, it's a collection of all the partial derivatives. So somehow it's like, well, if you take the partial derivatives and combine together, that's the derivative. Or you can think of the total is the sum of the parts in some sense. That's sort of the philosophy. Now, this is the idea for functions of two variables, but the same thing translates into functions of three or more variables. Any number of variables you have, you just simply say, look, for however many variables I have, that's how many partial derivatives I have, and I put them all together, and things work out rather nicely. So let's talk a little bit more about what's going on. First off, let's start with notation. So this upside down triangle symbol, it actually has a name, and we'll call it various things. One thing you'll sometimes hear is del. So you might hear it called del f. Or you might hear something called the del operator. We'll come back to that in the future. And so what is the upside down triangle, or del? Well, you can think of it as just a vector, which is saying in the first slot, take the derivative with respect to x. In the second slot, take the derivative with respect to y. And in the third slot, take the derivative with respect to z. Now, there's another name that you might hear, and it depends on where you're at as to whether or not you'll hear del or nabla. So that's the other thing, nabla. Now, you might say nabla, that's a weird word. I don't know if I've heard that one before. But actually, if you know what it comes from, it helps to understand the symbol. So, in some sense, it comes back to this notion of a Greek harp. And So if you look at the Greek harps, well, you have to imagine some sort of mythological small deities, and they would play this harp. It would be a little triangle, so you'd have these little tiny strings going down, and that was nabla. That's what it was referring to. This idea of also tied to sort of this harmonic notion going on with the harp. Okay, so if you think of this del as being the collection of partial derivatives, you can think of this, the gradient, the gradient of f is multiplying this operator del by f. So partial x, partial y, partial z of f just says take the partial derivative in each slot. Now, because partial derivatives are derivatives, they have nice properties. Things like derivatives are linear, and therefore this gradient is linear. So if I have the gradient of f plus g, it's the gradient of f plus the gradient of g. You can pull constants out of derivatives. So you can pull constants out of gradients. You can do product rules with derivatives. In other words, you can do product rules with each partial derivative and say, look, entry by entry, I have a nice product rule, and therefore when I put it together, I get a nice product rule for gradients. So the gradient of f times g is f times the gradient of g plus the gradient of f times g. And you can even do chain rule. Gradient of f of g of xy is f prime of g of xy times the gradient of g of xy. All sorts of things. So in other words, the kinds of things you would want a derivative to do, that's what the gradient is doing. And this will be a really important idea, especially as we get to the very end of the course. So there's a lot of good stuff to look forward to as we get towards the latter part of the course. But for now, we have one goal for today, which is we said, okay, we have this notion of a derivative. Now can we talk a little bit more about a derivative in a particular direction? So that's our thing for today. Now, in some sense, we've talked about derivatives in particular directions. So we have this partial derivative. Partial f, partial x answers the question, how does f change as we move in the x direction? Partial f, partial y says, well, how does the function change as we move in the y direction? So we can visualize this in some sense. So what's going on, the picture here you should be thinking of is I have my three-dimensional space. So there's my three-dimensional space. And I also have above here some sort of surface. Now the surface is really a function. So here I have my function. Z is f of x, y. Now our question about what's happening, what's the change, is really saying, suppose I have a point downstairs, here's my point downstairs, and I say, what's happening upstairs? Well, when I talk about the derivative with respect to x, that says, well, I'm going to move in the x direction. So in the x direction, that's this slice here. So it's saying, well, what's happening as I move in the x direction? When I talk about the derivative with respect to y, well, that's asking the question, what's happening as I move in the y direction? So the y direction is here, and that's this slice. So I have, okay, well, maybe in the y direction, I have some other behavior. But you might say, well, those are only two directions. We have many, many more options to choose from. So I can ask the following question, namely, why not go in some other direction? So in other words, I want to say going off in some way. So the question becomes, well, how do we understand that? Well, that's a good question. Now, first off, as always, we can swing back to single variable calculus and say, well, what was the idea back there? Because there was an idea of a directional derivative. We had what we called left-hand versus right-hand derivatives. And in the idea of the left-hand derivative is what's happening on the left-hand side of that point. And for right-hand derivatives, we had what was happening on the right-hand side of the point. And therefore, we said, oh, we can look at those two sides. Well, here we can say, look, I now want to understand what's happening in any direction. So if we think about what we did with the left hand and the right hand, we said, well, just focus your attention only on that side. So if I want to go in a particular direction, what we can do is we can say, well, you can almost imagine the following. Just look at what's happening above. So in other words, if I'm coming out from my point in a particular direction, I can say, look at the surface that lies above here. What is it doing? And now I'm in a slice, or more particularly, I think it's more precise to say a half slice. When we talked about the derivative with respect to x and y, we were allowing ourselves to go in either forward or backward. Here, we want to say, look, we're only going in one way, in that direction. And the question becomes, okay, what's happening in that slice above? What's the change? What's the function doing right there? Okay, so in some sense, it's a reasonable thing to do. Now, how do we think about it? Well, let's think about what's happening with our normal directional derivatives. We say, look, partial f partial x, that says what? There's a definition for it. You take x plus a little bit, comma y minus f of x. In other words, we just perturb in the direction of x and ask what's happening. Okay, well, if I have x plus a little bit, comma y, if I think of my point as being x comma y, then I say, okay, what's really going on here is I'm just taking my point and I'm perturbing my point plus a little tiny amount. So h says perturb a little tiny amount. I says in the direction corresponding to the vector I, and I is the vector that says move in the x direction. When we look at partial f partial y, very similar thing happens, except we look at y plus h, which says, oh, I'm perturbing in the direction j, which is the direction that points in the y. So here we go. Here's how we're going to understand this. Namely, when we talk about a directional derivative, so our notation here, d is shorthand for directional derivative. Sometimes in general, if you see a capital D, it's a shorthand for derivative. Not a surprise. U, well, that is a vector. And that's a unit vector which indicates direction. If we're going to talk about directional derivative, we have to have a direction. And the way we represent direction with vectors is unit vectors. Then the other parts are not so hard to imagine because you have your function, which is your f, and of course you have where are you at, because when we talk about a directional derivative, it really means a rate of change. And indeed, we shouldn't get used to the idea. Rate of change is just a fancy way of saying derivative. So here we go. What is it doing? Well, it says, look at the function at the point P where we perturb it in the direction u by a small amount. How much? By h. So in other words, we went from P and went out a little bit in that particular direction. And then said, okay, now compare it to just the function at that point and divide it by how far you went. So it is, in essence, you're taking a derivative in that half slice. Now, why do we say a half slice? You'll notice I'm only allowing h to be positive. So I'm only coming out in one way. All right, good, good. So we can look at directional derivatives. Now, I want to point something out here. It is possible for a function to have a directional derivative at a point and to not be differentiable at that point. We can think back to the analogous thing that happened in Calc 1. So in Calc 1, what was our sort of go-to example? What's the function that we know doesn't have a derivative? Well, in Calc 1, it's our absolute value, where that v comes together. Because no matter how far you zoom in on that tip, it's still going to be sharp. There's still going to be at that point. So what's happening when we talk about multivariable functions? Well, the easiest thing to do is to do something like the following. Namely, have something that comes down to a sharp point. And an easy function that does that is the cone. So if we think about the cone, well, it comes down to a nice sharp point at the origin, and it does have a directional derivative from the origin, because no matter what direction you go, you're going up. So you can talk about, oh, I can always go up in any direction. But it is not differentiable at the origin, because no matter how far you zoom in, it's still going to look like a sharp point. And so directional derivatives does not have to be where our function is differentiable. But you might say, okay, what if our function was differentiable? Is there a nice way to take our directional derivative? And in particular, fingers crossed, can we get rid of the limit? Because one of our ideas that we often come across is like, limits look scary. I hope we don't get too caught up in that, because limits aren't meant to look scary. We want to get comfortable with using them, but we'd also like to have to not use them if we can. So we've got some good news. There is a way to do it without taking derivatives if our function is differentiable. Now, why? Well, if our function is differentiable, the thing is that locally it's a flat thing. And remember that when we talk about derivatives, we only care about what happens locally nearby. So we say, since it's flat, I can replace the function by its tangent plane. So what happens? Well, we can say, look, f of xy minus f of ab is approximately what happens on our tangent plane. Partial f partial x at ab times x minus a, partial f partial y at ab times y minus b. So again, this is just a philosophy. I know I keep saying it over and over again, but I say it over and over again because it's so important. The idea that if we look close, things are flat. And flat things are good. We like flat things. All right, now let's just really hone in. We're going to have our point be the point AB. All right, have our vector. It's something, I'll call it ST. And so that the point plus a small perturbation in the direction of our vector u, so h, think of as a small positive quantity, is what? Well, it's a plus h times s, b plus h times t. No surprise. I know where I'm starting. I'm starting at AB. I know I move this way a little bit. I know what the amount of movement is, so I know where I end. All right. So we come to the conclusion, p plus h times u. Whoop. This should be a bold u. I'm sorry about that. There we go. Minus f of p is, all right, now we apply our rule. Partial f partial x at ab times hs. Why? Okay, that actually comes back to our idea of what's happening here is that this part is change in x. And so our change in x is the hs. And of course, similar thing happens with the other entry. The y minus b, change in y. So that's the h times t. So the rate of change in the x direction times the amount of change in the x direction plus the rate of change in the y direction times the amount of change in the y direction. Well, now we say, look, h is common, pull it out, and what we have left is the partial derivatives dot st. But wait, partial derivatives has a name. It's called the gradient. St has a name. It's called u. So we end up with h times the gradient dot u. Now, you'll say, great, wonderful, except, of course, Steve, you have all these squiggly lines. That just means it's approximately that. And the answer is yes. But the idea of differentiability says, as I get closer, approximation gets better. And so when I talk about taking limits, approximations become equalities. And notice what happens. If you divide both sides by h, you end up with the gradient of f dot u. And that's it. A beautiful answer So on almost any function that we have, that's a reasonable function, in other words, one where we can take derivatives, it's super easy to take a directional derivative at a point. So what do? We figure out what point we're at. That's almost always going to be given. We figure out what direction we have. Now, for direction, it can be a little bit subtle. They might give us a vector, but it might not be a unit vector, so okay, divide by its length. Or they might say from this point to that point. Well, then we turn it into a vector, and then we turn that vector into a unit vector. But at any rate, we can figure out what our unit vector is. So we have our point, we have our unit vector, and then we take the gradient, and we say, okay, here's our gradient, evaluate it at our point, dot it with our unit vector, and life is good. So taking directional derivatives, very straightforward, lots of fun, and just a matter of being patient, and we can get our answer. So I suppose now it's time for us to go and do some practice. So hope to see you soon. Bye.